talk about the title here, but she spoiled me the title of the talk. I didn't want to give you the title of the talk at the beginning because I was afraid that I would scare you, because this is an experimental talk. So the first thing I wanted to tell you was actually the conclusion of the talk. So, and this doesn't work, here. So the conclusion and the only take-home message that I would like you to remember from this 30 minutes is that this platform, is a very good platform for studying quantum thermodynamics of non-equilibrium systems. So before trying to convince you in the next 30 minutes, let me give you a little bit of an understanding of what I mean for good platform to study quantum thermodynamics of non-equilibrium systems. So for me, a system is a mechanical object that lives in a given potential landscape, that acts through this potential landscape, and then it exchanges energy interactions with an environment. And it exchanges thermodynamics quantities, as it can be entropy, information, heat, work, whatever. And when I say that this system plus environment is quantum, I mean that they both act following quantum mechanics formalism. For example, a system that is a wave function that evolves through Schrödinger equation is a quantum system. A photon that interacts with this system and acts as an environment is a quantum system. And when I say that non-equilibrium system, I mean we are looking at transformations, thermodynamics transformations of this system, so that the system is not in equilibrium, not in thermic equilibrium with the environment, meaning that we are looking to transformation that have usually an associated change of entropy. Now, before starting the talk, let me break down the image of the experimental platform for you. This is mainly divided in two parts. An optical tweezer that levitates one or more nanoparticles. Optical tweezer is an outstanding tool, and Ashkin won the Nobel Prize for it this year. And the main catch is that we are using optical tweezer controlled by SLM, meaning that we tune the potential in which the system lives in. The nanoparticle is trapped in vacuum. It means that I can tune, by changing the pressure of the surrounding environment of the gas, how much interaction I have between the particle and the environment, how much thermal interaction I have. And the second part is cavity optomechanics. The particle is trapped along a cavity, and this creates an interaction between the optical mode of this cavity and the mechanical mode of this particle. This is incredibly interesting because the cavity, so changing whatever drives the cavity, so the optical modes, allow you to change and to control the interaction between a certain reservoir given by the cavity and the system. And if you are good enough that you manage to remove the energy from the system, you can actually think about going into the quantum regime, in which the system is so slow that only have one photon of interaction, and means that it evolves using quantum formalism. Both together maximize spatial and temporal control of the platform and allow you to give full control over the potential landscape, meaning the system, and of the environment, meaning the reservoir. So now I can give you the title of the talk, which is Optical Levitation in Far From Equilibrium System Toward the Quantum Regime. This title can be divided in three parts: optical levitation, which is the experimental platform we use; far from equilibrium system, which is what we are interested in; and toward the quantum regime, which is the ultimate goal. The talk would be divided in three. First, let's start with optical levitation. Why is it interesting? Optical levitation is, in principle, fairly easy to understand. You take a laser, you focus this laser, you create a gradient in the electromagnetic field, and this comes with the creation of elastic forces. So if you put something and you put it in the middle of where your laser is focused, this something, if it's soft enough, if it's small enough, will stay there. If you put a particle in the focus of the laser, you basically have three main forces that act on the particle. Gravity, that pushes the particle down. Radiation pressure, photons that go to the particle and try to push the particle away. And then the elastic force from the fact that you have a gradient in the electromagnetic field. If the particle is small enough, then the elastic forces are the dominant contribution, so that you can actually ignore gravity and radiation pressure. But optical the key word for this mechanical system is that if you focus something different from a normal, boring Gaussian beam that creates a parabolic potential for the particle to move in, you can create different potentials and nonlinear potentials. So the main point here is that I will change the wavefront to change the potential shape. Second is that optical levitation can be also seen as a thermodynamic system per se, meaning that you have this particle, and the particle will have a certain temperature, which is defined by the center of mass motion of the particle itself, and then the particle interacts with the surrounding environment that's made by air molecules. If the two temperatures are different, whenever an air molecule goes against the particle, there will be a transfer of energy between the particle and the environment. Whatever changes the temperature of the particle interacts with the system, creates a damping effect in the oscillation of this particle. Of course, if the pressure is high enough, the main interaction will be the one from the air molecules. But then if you start sucking out the air so that you decrease the pressure in your system, the contribution by the air molecules becomes smaller, and then you will see the contribution by the radiation damping, meaning the photons that exchange energy with the particle, and so on if you put feedback or external drive. The main thing here is that the damping gives you a certain coefficient, this gamma, that takes into account all the contributions, and 1 over this gamma gives you a time scale in which the particle thermalizes with its environment. The key word here is that if you control the damping, you control the interactions. Optical levitation has been used an experimental platform since some years, I would say less than 10. There are different experiments that look to cooling the particles, studying bistable potentials, studying stochastic dynamics. But I don't have the details to go through that. But if you are interested, I really suggest you to read this review from Jan Giesler and James Millen, which is Levitated Nanoparticles from Microscopic Thermodynamics. Gives you a good perspective of how levitated nanoparticles are interesting for thermodynamics. Let's move to the second part, which is far from equilibrium system. So we are not still there to create that platform that allows you to study quantum thermodynamics. Otherwise, we would study quantum thermodynamics. But in the meantime, we still have something interesting to see. All the parts of this platform allow you to study different perspectives on stochastic thermodynamics. I have a few examples for you, but for a matter of time, I will just show you one that incidentally is also the one I'm working on, and it's also the best from all the experiments that we have in the group, of course. So I will show you Landauer principle in non-equilibrium that takes advantage of having the optical tweezer with no linear potential. I'm sure everyone here is fully aware of what Landauer's principle is. If you have a memory, can be either 0 or 1. You do something to this memory so that you erase the information about the memory. Then this cannot come without heat dissipation, which is bounded by KT logarithm of 2. Landauer's principle is incredibly interesting, at least for 2 reasons. The first is that it's a fundamental link that links information and thermodynamics. And the second is that experimentally, practically, whenever you have a computer and you erase the information, you have an hard disk and you format it, it comes with an energy cost. So transistors are becoming smaller and smaller, and they are coming close to this bound. So studying what this bound is actually interesting. Main point here is that an optical potential and trapping a nanoparticle is very useful to study problems like Landauer's bound. Suppose that you manage to optically create a double well potential where the particle can either be on the left or on the right, 0 or 1. And you have access to the potential, so you can fully control the shape of this potential. Then what you have is a memory. And if you can change this potential, you can actually perform protocols that erase the information about this memory. So suppose that you start with a particle that can be either on the left or on the right, and you manage to decrease this barrier in the middle. You decrease it. At a certain point, you lose the information of where the particle is. It's neither on the left or on the right. Then you introduce an external force, which is the thing that actually does work on the system, so that you push the particle on the left, for example, and then you increase the barrier again. What you've done is to erase the information about the particle position. Actually, what you've done is that you took a particle distribution, a phase-space particle distribution that could have been either on the left or on the right, and after a given thermodynamic transformation, you just halved the phase-space distribution. And this comes with an entropy reduction because you halve the phase space, and this, in order to saturate the second law, you have to compensate it with some heat dissipation. So in 2012, Nature paper by Beruth and others verified Landauer's principle linking information and thermodynamics with this result here that actually shows you that you can saturate Landauer's bound. The slower you are, the better you can saturate. Meaning that if you manage to do this transformation fully in equilibrium, so a transformation that is fully reversible, then you manage to get to kT logarithm of 2. The question we are trying to answer is a little bit different. And it's what happens to Landauer's bound when you get out of equilibrium. Again, two reasons why this is an interesting question. The first is that it's philosophical. Landauer's principle is fishy somehow because it's an asymmetric law. It gives you a bound on how much energy you need to erase an information, but it tells you that in order to encode this information, you need 0 energy. So it's something strange. And on the other end, the practical reason is that equilibrium memories are not the only memories that exist. In your computer, you have the hard disk. This is an equilibrium memory. You plug the outlet off, and the information will stay there. But you also have RAM memories that are non-equilibrium memories that are incredibly faster, but they require energy in order to be encoded. So what are the bounds in order to study RAM memories? This is interesting. Now, Michael, Konopik, and Eric, with the assistance of Nikolai, studied the bounds in non-equilibrium. And you can actually see here that average work and heat are still bounded by kT logarithm of 2, but then there is this new contribution here, which is this I of tau and I of 0, which is basically the information entropy of your system, of your particle, whenever it's in the non-equilibrium condition and when it's in the equilibrium condition. And then heat is modified by this delta U that actually tells you how much energy you need in order to encode the information in non-equilibrium. So the main result of their paper, Konopik here, it's in the archive and it's from the last year, it's that the more in non-equilibrium you are, this is given by this parameter epsilon, the lower the work and heat you need in order to cancel the information about your memory. And the cool thing is that there is actually a bound in which the heat dissipation goes below 0. So this is what we are trying to test, and I will not show you the results because we have data, but we still didn't analyze it, and I have Tobias back in the lab right now trying to get sense out of those data. But I can tell you why experimentally this is interesting and why it should interest you. The thing is that using optical tweezer and using this guy here, which is an SLM, I can change the potential that goes through this SLM and then it's reflected in order to have whatever potential I want. For example, if in this SLM I program it so that I have an hologram that divides the beam in two and gives a 0 phase shift on the left and a pi phase shift on the right, then I can create a TEM01 mode, which is exactly the double well I need. So once I have this tool at my disposal, I can show you what an experiment look like. You have the trap here in the vacuum chamber. You have here the lens that creates the trap. And here you have the SLM. The SLM changes the one given polarization, let's say the vertical polarization, from the TEM00, the Gaussian beam, to the TEM01, the double well. And what I do is that I go to the SLM by modulating how much horizontal polarization and how much vertical polarization go to the SLM. And changing the balancement between H and V, I actually change the shape of the potential by lowering or heightening the barrier in the double well. This is actually how the experiment looked like, but not particularly interesting. What I can tell you is examples of protocols that we already have. Let's say that you have the particle. Let's start here. This is position of the particle against time. And this is one protocol. The particle can either be here on the left or either be here on the right. Then you start the protocol. The particle goes more or less in the middle. You lose information about where it was. Then at a certain point here, you have the force acting on the particle, and then the particle finishes on the right. And then you repeat the protocol again. And again, left, right. And then again, from right to right. And then again, from right to right, and so on. And then you take average work, average heat from these distributions. In order to reconstruct work and heat from a distribution, you basically need two things. Velocity, square velocity, so kinetic energy of the particle, and this comes from measuring the position of the particle in time, and the actual shape of the potential that requires additional measurements. What I can tell you is that the success probability of our protocol is more or less 90%, meaning that actually it works very well. Now, the thing that interests you is that, yes, I can do the double well. This is so cool, but it's only a double well. But I can program this SLM in order to put whatever hologram I want into this SLM in order to create whatever potential I want. So for example, if I'm interested in studying the motion of the particle in an x to the 4 potential, like a box, then I change this hologram here, and then I have an x to the 4, and so on. So the limit of this platform is more or less the imagination that you have, and you want me to try with an experiment. Now, toward the quantum regime is the last part of the talk. So how do we get to the quantum? For now, everything was classical. I need to show you a little bit of optomechanics. So I'm not an expert on that. I basically learned about optomechanics 5 days ago while creating this talk. But it's easy. You have light and you have a mechanical system, and you have an interaction between light and mechanical system. Light modifies this mechanical system somehow. The mechanical system being modified modifies the light somehow. So there is a feedback between light and mechanical. This allows you to create interaction between light and mechanical system. Again, this doesn't work. Okay. So even easier to understand, you have, for example, a mirror that's connected to a spring. You have photons going into this mirror. The photon gives a certain momentum to this mirror. The mirror goes a little bit back by the effect of this photon, and the photon is reflected. Of course, this kind of movement is incredibly low, and you cannot measure it. But in principle, the photon will get a phase out of the fact that the mirror went a little bit farther away. So what you do is that you increase the interaction between the photon and this mirror. So you create a cavity. You put a cavity here so that the photon starts to go back and through between the two mirrors of the cavity. And now, every time it bounces through the mirror, it gets a little bit more of this phase. So that when the photon actually exits from the cavity, now it will have a phase that you can actually measure. So the enhancement given in the interaction between phonon and the mirror is amplified by the quality factor of this cavity. Of course, this is true for the mirror in a spring. It's also true for a nanoparticle in a cavity. Again, you are bouncing photons to this particle, and the particle is starting to move, caused by these photons. The interesting thing here is that whenever you expect this particle to have just like one phonon of interaction, of excitement, the movement you expect of the particle is 30 picometers, which is incredibly low. Now, why is it interesting to have a cavity? It's interesting because it gives you access to a set of quantum toolbox to prepare and control mechanical states, mechanical quantum states, by means of controlling photonic quantum states. The catch here is that controlling photons is easy, while controlling mechanical states is hard. So let me give you an example. Suppose that you have this cavity, so this system here, and you actually have the resonance frequency of this spring here, omega m. Then you have a resonance frequency of the cavity, and then you have this laser that interacts with both. Now, if you change the frequency of this laser so that you go with a frequency which is higher, like you send blue photons into the cavity, with omega of this laser being omega of the cavity plus omega of the spring, then you are actually simulating a parametric down conversion effect. A blue photon becomes one red photon that resonates with the cavity plus one phonon that is added to the spring. And again, vice versa. If you go with a photon which is in the infrared, you actually are sucking out phonons from the system. So this gives you a tool, for example, for cooling the nanoparticles without actually even measuring it. You just put a red detuned pulse into the cavity, and then you will see the motion of this particle becoming slower and slower and slower because you are sucking phonon out of it. So it gives you access to these Hamiltonians, which are the beam splitter Hamiltonian, the quantum, the QND Hamiltonian, and the squeezer, that allows you to create fancy quantum interactions between phonons and photons. In order to actually say that you have a quantum object, you need to say that the interaction of your mechanical system with the cavity is larger than the interaction of your system with the environment. If you manage to do that by tuning the parameters of this cavity, you reach what we call the strong cooperativity regime. Basically, if this number here of that depends on your cavity, your interaction, your particle, the shape of the particle, whatever, is greater than 1, then you can say that you can actually manage to cool your particle to less than 1 phonon of excitation, meaning that you can actually treat it like a quantum object. All the things I'm saying are not just out of the blue. They've been demonstrated, and they are being demonstrated to be an actual tool that one can use in order to control mechanical motion. So there have been experiments for everything, except, of course, for going into the quantum regime, which is something that in the laboratory of Marcus Aspelmayer, they are trying to do, and in principle, they should be close to achieve it. Okay, there have been a couple of experiments about cavity cooling. You believe me if I say that different experiments managed to cool a particle from the 300 Kelvin to 100 phonons or so. I tell you what a system looks like. This is David. This is the system. This is a nanoparticle which is trapped by an optical tweezer. So the white spot here is the nanoparticle. Now we only have the optical tweezer. What David will do is that he will manually introduce the cavity into the setup. Let's see if it works. Does it work? Yes, it works. So here is the cavity. So it actually puts the cavity in, then it closes everything, then it goes down in pressure in order to reach the vacuum, and then starts driving the cavity. So this is the setup we are using. Okay, again, a particle in a cavity can be cooled by red detuning, detuning the driving laser. You believe me, it's possible to cool this particle. So everything I said, it's true and it works. But let's stop here. Let's go back to the beginning. And I showed you that this is the platform we have. And this platform can be divided in two. One part controls the system by controlling the potential landscape and going into the nonlinear potential landscape. And this other part actually makes you go to quantum regime, and it controls the interaction between the system and the reservoir. So if you remember, on Monday, the discussion panel, you guys asked for different things from an experimental platform. And among all that came out, you had the requirement of realizing a non-equilibrium bath beyond thermal. This platform can do that. You remove all the interaction with the thermal environment, meaning the molecules, and you tune the interaction by using the cavity. You wanted the characterization and experimental measurements of entropy production. Indirectly, you follow the movement of this particle, you track the movement of the particle, you can reconstruct how much energy you have before and after transformation. So it gives you the measurement of entropy production. You wanted two bodies with interaction. Well, no linear potential, for example, a double web potential means that you can trap two particles and see the interaction between the two particles. For example, an electrostatic interaction if the particles are charged. And then time scale. As I said, tuning the interaction between the system and environment gives you a control over the time scale the particle needs in order to equilibrate with this environment. So in principle, all these four requirements are accessible from our system. So back to the future, this is a very good platform to study quantum thermodynamics of non-equilibrium system. Not only the goal is interesting, but also how we get there, because all the platform by themselves allow you to study interesting thermodynamics. And I conclude by showing you our group. This is Nikolai's group. This is Marcus in the middle. Not really Marcus, but come on. Tobias, Mario, Marcus, Michael, which is basically part of the group in some sense, Nikolai and Maxim. This is the boring acknowledgement slide. And with that I conclude. So thanks.
Questions?
Hi, this